Okay, here's what I want you to do in this video. You'll notice I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 different elements here. I want you, here in just a second, I want you to pause the video, and I want you to come up with the Lewis dot structure. Now I'm going to give you a helpful hint before you take off. If something ends up being full, and it doesn't happen very much, but when it does, let's say element X, you end up with something like this: 1, 2, 3, 4, 5, 6, 7, 8. Now, is that logical? Well, if you remember in middle school, 2 go in the first ring, 8 in every ring after that. That sort of goes with what we've learned. Now, X is an unknown element. There's no such element on the periodic table that's an X. But you just put them around until you've used up all the valence electrons. So here's what I want you to do. Whether you draw atoms like this with the rings and put the electrons in, or whether you do it in electron configurations, I want you to come up with the valence electrons for each and draw the Lewis dots for each of these, and we'll come back and check your work. So go ahead and pause the video. We'll come back here in just a minute. All right, now I'm going to write out the first couple, and then I'll just give you the answers, and we'll see how you did. Potassium is element 19, right here in column 1. And so if you wrote out the electron configurations, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. If you wrote it all out, that's what you would end up getting. So that means potassium has 1 valence electron. Now it can look like that. You could have put it at the top, on the left, or the bottom, but there's only 1. That's going to be very important when I come back to that one in a minute. We'll go ahead and put a star because that's going to be important to us. If you jumped over and did oxygen, again, I'll write the electron configuration: 1s2, 2s2, 2p4. And again, it becomes very logical as you look at the chart. Second Street, P section, 1, 2, 3, 4, 2p4. But both of these are in the P section, so that means it has 6 valence electrons. So if you're going to get this right, it's going to look like this: oxygen, 1, 2, 3, 4, 5, and you can pair up with any of those 3, but that's all you have. 1, 2, 3, 4, 5, and then I started pairing 6. So it's going to look like that. Now, you could have had your 2 pairs on top and left, or top and right, or top and bottom, or left and right. Doesn't matter, but you should have 2 pairs and 2 singles. That's how it ends up being correct. All right, so let's check your work from here on. Chlorine should have had 7. 1, 2, 3, 4, 5, 6, 7, if you got that right. Nitrogen should have had 5. 1, 2, 3, 4, 5. 1 pair and 3 singles. Sulfur should have had 1, 2, 3, 4, 5, 6. Beryllium should have 2. That's what that looks like. Carbon has 4. 1, 2, 3, 4. Sorry, I wrote that wrong. Sometimes written singly like this, but typically the way we were doing it: 1, 2, 3, 4. And I could put those dots wherever I want it. Mg had 2. 1, 2. Neon had 8. 1, 2, 3, 4, 5, 6, 7, 8. Aluminum had 3. 1, 2, 3. And those are what all of them look like. If you're struggling with that, go back and watch the first video. But those are the valence electrons. Now I want to show you a couple of things that are super important. You'll notice I put a star here. If you go back and look at your notes, that looks just like sodium. The only difference was sodium was Na with a dot. Now why would that be logical? Well, this is going to be super helpful and a reminder. Sodium and potassium are in the same column. So that means they both had the same number of valence electrons. There's a reason the periodic table looks like this. As a matter of fact, if you want to on your chart, I bet lithium, let's try it out, lithium with 3. If I had lithium, let me cram it in right here real quick. Lithium had 3. That's 1s2, 2s1. That's 1 in the outside. You'd have Li with 1 dot. Also, everybody in the first column has 1 valence electron. 1 valence electron. Okay? But you'll also notice this. Chlorine. This one right here looks just like the chlorine we drew a while ago. Huh. Logic. Okay, let's see if we can figure out a pattern. If you look at beryllium and magnesium, look how those things look alike. Beryllium and magnesium, they're right here. They had 2 in the outside ring. I'm starting to pick up a pattern. Aluminum was right here and had 3. Carbon was right here and had 4. Nitrogen's right there and had 5. Oxygen and sulfur I purposely picked them to look alike. Notice they look the same. They had 1, 2, 3, 4, 5, 6. Notice I put the pairs in different places, but I had 2 pairs and 2 singles. And that was 6. Chlorine was 7. We already saw that. Neon was full with 8. So you don't really have to memorize a whole lot. All you have to do is use your chart. So if I asked you how many valence electrons does a rubidium have right here, the answer is 1, because everybody in the first column has 1. If I asked you how many boron has, he has 3. So I already know valence electrons as I count left to right. Now notice we skipped all the short columns. Remember, this section right here, and you don't have to write this on your chart, but this section right here up to the staircase are those transition metals. They don't ever follow the rules of everyone else. The tall columns have a pattern. The guys in the middle, in one of the other videos, I'll talk about these transition metals. But everybody else follows a pattern. Everybody in column 1 has 1 valence. Everybody in column 2 has 2. Everybody in column 3 down to the stairs. Now remember, we've drawn this staircase. You already have it on your periodic table. These guys have 3. Okay? 4, 5, 6, 7, 8, all the way to the bottom. Now remember, these are called the noble gases. Noble gases are already full. That's logical. We just proved that with neon right there. And everyone in that column. Now it would be hard to draw out xenon with 54 electrons, but if we follow the pattern, there's a reason they're in the same column. So when you look at the periodic table, it becomes your biggest tool because it puts elements together that act the same, react the same, the atoms are built the same. And it's very, very true here. 1 valence electron, 2 valence, all the way down. 3, 4 to the staircase, 5 to the stair, 6 to the stair, 7 to the stair. Now, why do I say to the stair? Because after you get under the staircase, you're in these transition metals, which are these 3 lines. Now, being tricky here, watch carefully. Boron and aluminum both have 3 valence. Oh, he's under the stairs, but he's not in the transition metals. He's close. He lives right near them. So he has 3 valence also. 3 valence, 3 valence. Now the valence electrons could be super important. So hopefully you got these valence electrons right and you got the Lewis dots. In the next video we're going to see how we start using these things to make compounds. You're doing great. Keep it up.